of the topic of my talk today. So the great part of my work is developing computational models for biological systems, in particular for biological systems that are suitable for a network representation. Which is the goal of the work that I like to present you today. So the goal is to analyze a biological system and to detect the presence of deterministic chaos in this system, if, of course, there is any deterministic chaos in that system. So what is deterministic chaos? Because these two words seem to be in contradiction, of course. So we say that a system is affected by deterministic chaos if its dynamic is governed by deterministic rules, but the system is highly sensitive to the initial condition, no matter how small the variation of the initial conditions are. So this means that after a given period of time, if the system is sensitive to small variation of the initial condition, the dynamics, the behavior of the system becomes unpredictable. It's very important for a biologist, for any practitioner in computational biology, to know the extent to which a biological system dynamic is predictable. I imagine that the concept of deterministic chaos can be a bit obscure, even if I give this simple definition. So I would like to give you also a simple example from physics of a system affected by deterministic chaos. Here in this slide you see the famous example of a double pendulum. So we actually have two pendulums. You see that the first part, so the first end of the pendulum is following a circular trajectory, so a very regular trajectory, but the second end of the pendulum is tracing noisy, arbitrary trajectories, because this system is very sensitive to initial conditions. So if I disturb the system also with small disturbances, I can change a lot the trajectory followed by the second end of the pendulum. An important case is the case in which the system is affected by low-dimensional chaos. This is the most interesting for us, because low-dimensional chaos means that the system is still affected by chaos. So it is very sensitive to initial condition, but only a small number of its components have a chaotic dynamics. Okay, so this is essentially the introduction, the definition of the topic of this talk. Why study chaos in biological system? And in particular, why studying low-dimensional chaos in biological system? So we have said that we are talking about chaos that is something very different from noise. This is important to highlight this point, because the system is still deterministic, but it is affected by chaos. But if the system is deterministic, it means that, after all, the system can be controllable, because I have in my hands the rules, so the equations determining its dynamic, and these equations do not contain any noise term. In particular, if a system is affected by low-dimensional chaos, it means that there are few drivers of the dynamics, so there are few components of the system that are responsible for chaos. And if a system is very large with many components, but it is affected by low-dimensional chaos, it means that I have probably a good chance to control the system acting only on a few number of its components. controllability of biological system is important when first, when I want to interfere with this system, and there are a lot of fields in which we may want to be able to interfere with the system. I will explain you later one important case in which we may want to interfere, we may want to control the system, and so we want to identify if the system is affected by chaos. First of all, let's try to see which are the mathematical tools in our hands to solve the problem to detect deterministic chaos in biological system. We have a very powerful tool in our hands, explained in many textbooks, and the tool is the phase space analysis of the system. For those of you that are not familiar with this terminology, phase space is the space generated by the variables of the system. So you can imagine a space and the axis of this space indicate each variables of the system. So in general, phase space is multidimensional for very large system, okay? Then we have another common, very well-known tool to explore presence of chaos. It's the tools of sensitivity analysis. And then we have other more sophisticated instruments in our hand to detect chaos. We have the so-called complexity indices. They are in particular Lyapunov exponents. Lyapunov exponent is an index that quantify the rate of separation of infinitesimally closed trajectories. So if we are saying that the system is sensitive to initial condition, we can imagine that if we change slightly the initial condition, I generate another trajectory of the dynamic. So the rate at which the separation grow in time is quantified by the Lyapunov coefficient. Then we have the fractal dimension. That's essentially it's a statistical index measuring the distance, the pairwise distance between the time point of our time series. Remember that when I talk about dynamics, I'm talking about time behavior of the system. So practically in my hands, I have the time series describing the change in time of some feature associated with my system components. So essentially, it indicates, so if I measure the distance between points of time series, at the end I'm measuring how the trajectory of my dynamics fills the space. So how much space it occupies and in which way this trajectory occupies the space. Then I have sample entropy, another important index that is measuring the noise, essentially in my dynamics. Low sample entropy means that my trajectory is not so noisy. Then I have time lag. Time lag is essentially the time after which the autocorrelation of my time series becomes negligible. And then I have the embedding dimension. This is even a more sophisticated index. By embedding dimension, we mean the minimal dimension of the phase space in which trajectories of the dynamics do not cross themselves. So the minimal space in which the dynamics is still non-affected by chaos, essentially. It's not so complex, so irregular. So in order to perform phase space analysis, sensitivity analysis, and the calculation of all these complexity indices, I and my collaborators developed a software tool in Python. And we use the most modern and advanced libraries in Python. We use SciPy, NumPy. We use also AppJar to create a comfortable interface for the user. We use matplotlib if the user wants to draw plots, and we use SciPy. And this is my favorite library in the sense that as a physicist, I almost write formulas on my notebook with the pen, and I would like to have a library, a tool that allows me to write again my formula in mathematical like style. So using mathematical symbol, the same that I'm using on my notebook. I imagine that this is almost unreadable, unfortunately, but let me only explain the main part of this code. I have only 2 slides on codes, just to show you how simple is the code using Python with respect to other languages like C++ or even R, that is now starting to be used as a tool also for solving differential equations. The code has a module that solves a set of differential equations that describe the dynamics of my biological networks. And by solving differential equation, it means that I have to perform numerical integration of this equation. This is how the code looked like. It was simpler and more convenient in my case, use essentially the NumPy array specification of my differential equation. I will explain you later why. And then this tool has a module for the computation of the null clients, for drawing the quiver plot, so the plot of velocity, where it is possible, because all these plots are possible only in 2 dimensions. So if I have 2 differential equations, so for two variables of the system, if we have more than 2 variables, it's difficult to provide a usual graphical representation, and we have a more complex way to output the result of computational analysis of multi-dimensional phase space. The tool is equipped also with a module for the calculation, for example, of the steady states and the nature of these steady states. So the tool implements the calculation of Jacobian matrix to determine the type of steady state of the system, and the tool has and the tool output all this information in a file and also in a video in a GUI interface. In particular, the program in Python is able to output for the non-expert user the interpretations of these results, because a part of the target of our work is made by biologists, so people that do not have a background in mathematics, and so the work for us is not to provide results and stop there, but also to provide the interpretation of these results. So the tool is able to say, okay, we calculated the steady state, we calculate the eigenvalues of Jacobian matrix. If the real part of the eigenvalues of Jacobian matrix are positive, we have one type of steady state. If the real parts are negative, we have another type of steady state, because you know, the first case we have unstable steady state, in the second case stable steady state, and then according to the sign of the eigenvalues of this matrix, we can have stable, unstable, saddle points, and so on and so forth. So this just to say you that a large part of this code is also dedicated to explain, to interpret and explain the results for non-expert users. This tool has a name, and we have chosen chaos solver, meaning that we want to solve the problem of presence of chaos in our system. The tool is in two versions. The version which the command line version, like this one. These are examples of the plots that the tool can provide. So the plot of the dynamics in time. So on y-axis we have the variables that we are studying, and on the x-axis we have time. A picture of the phase space and the quiver plot. So the plot of the velocity in which we plot on each point also a vector that is the velocity calculated in each point of the phase space. So standard things for a mathematician, I know, not so standard things for a biologist that would like not to see all this complicated formula and prefer to work with an interface and then have an interpretation of results. So this is how the interface of this tool looks like. It's a very simple, it's just a skeleton and not so elaborated at this moment. It requires to input the name of the input file, and the input file for this system is the set of differential equations describing the dynamics of the system, and then there is a list of options to let to the user to select which results calculate. Do you want the dynamics? Okay, check dynamics. Do you want to make phase space analysis? Then check phase space, and so on and so forth. This is how the input file looks like. Okay. And this is the case study. So the case study is the Bacillus subtilis sporulation initiation network. And this is biological network composed essentially by three parts. So the parts of input signals, a part called phosphorylay, and a part about gene expression. So a bacterium can transform into a spore when the external conditions are no more favorable for life. So this is the part of the input signal. Temperature is not okay to remain alive. Okay, I have to transform myself in a spore. But the input signals from the environment are codified by a set of proteins in the phosphorylate module of the network. And this set of protein, suitably phosphorylated, modified, activate some genes in the bacteria that are responsible to the formation of spores. This is just to show you how complex and how many elements we have in each of these modules. And these are how the results of chaos solver are returned. This is the heat map showing the complexity indexes, okay, for each of the system components. So these very strange names here are the names of the nodes of my networks. Here you see the name of the complexity indexes, and here also I'm showing you also an analysis about the time behavior of Lyapunov coefficient, because it is very important to tell to the user, look, we detected chaos, and this is truly chaos, it's not noise. So it's important to show to the user if what we detect with strange complexity indexes is not noise but chaos. So non-linearity of Lyapunov coefficient in time is a sign of chaos with respect to noise, and so on and so forth. So a heat map is able to indicate to you which are the components whose dynamic is chaotic. We also report in table. This is only for this presentation. The software does not return this table, but we summarize, we process the output in order to individuate for each complexity indexes the set of system components that are scoring positive to that complexity indexes. And at the end, the tool is able to make an intersection of all of these sets, okay, of all of these sets, and to return the species that are scoring positive to the large amount of complexity indexes. So at the end of this long processing, the tool is able to say, look, for example, SPO0B, lacy, lacy T, SPO0B and SPO0A are the key driver of the chaotic dynamics. So you have a large network, only those components have a chaotic dynamics. So this is the final output of the cow solver. Cow solver, okay, the theoretical study before cow solver has been published in a paper on frontiers in microbiology 2 years ago. So in this paper you can find all the theoretical part and the definition of this quantity I have explained you. And I would like to thank the co-authors of this work that made a big effort in this project: Ivan Mura, Angela Re, Gary Barker, and Adoa Haiwaba. So it's an international team from Columbia University and from Quadram Institute in Norwich. This study has a great importance for companies of food research and for microbiology in general, because it's important, first of all, to know if the network governing the life of a bacterium is controllable or not, and which of the protein or gene components we have to touch, if it is possible, to engineer, to interfere the system in order to not produce spore, or in order to produce spore, or in order to kill the spore. This is important in food research for the conservation of food. It is important also in the study of many diseases, intestinal diseases, for example, especially in countries that are in poor countries in the world. That's almost all. If I was too fast or not very clear, please ask me.
Thank you. So if I understood correctly, cow solver is providing you as output in the case of regulatory networks, the output are genes. Yeah. Is it correct? Okay, so yeah. Genes which are supposed to be very sensitive to whatever variations.
Yeah, exactly.
Okay. And what about cases, I don't know, just thinking about right now, cases in which the unpredictable behavior does not come from a single gene, but, for example, a cluster of gene, is that a different problem, or, I mean...
that's an interesting question. I'm not sure which is the way to solve this problem. I have to be honest. But I can tell you what cow solver does in this case. So if a cluster of genes are responsible for chaotic dynamics, cow solver detects all these genes. Then cow solver is not able to say directly, look, these genes are in the same module in the network. But it can be easily implemented. So cow solver is able to detect all the system components, genes if we are talking about the gene regulatory network, protein if you are talking about protein, that are the key drivers of the dynamics, and if they are also affected by chaos. Of course, it does not tell you, look, all these proteins belong to this functional cluster in the network. You have to do work by yourself to say, oh, these genes that I have found belongs to a given functional module. This can be done. I'm not able at the moment to quantify the effort that we have to do, because we should take the network, the names of the genes or proteins returned by Chaos Solver, and then most probably mining the literature of the networks to discover to which functional cluster they belong. So Chaos Solver is not doing at the moment what is in biology is called functional analysis. So to associate to a set of genes their functions. It can be done. In principle, is not difficult. Maybe it can make the program more attractive to biologists. A bit too, maybe a bit computationally demanding if we want to follow the way of literature mining.
Just to understand, the software actually it's analyzing the dynamics of an analytical model.
Yeah.
So it's not about experimental data. In case you, so I wonder that for this complex system you have a model with equation of motion for each of these single genes.
Interesting question. Actually, you can work both with experimental time series if you have, or you can give to the system the differential equations. If you give the differential equation, you are able to calculate Jacobian matrix, for example, steady state, because they are solution of this equation. If you don't have the equation at the moment, Chaos Solver returns to you the complexity indexes. So it gives you Lyapunov coefficient, sample entropy, fractal dimension, and a very trivial representation, where possible, of the phase space, but at the moment not steady state calculation, because we don't have the equation. But it can work even if we give experimental time series.
Okay, thanks.
Any more questions? So, thank you.
Thank you again.
Our next talk would be fission track counting in mineral samples using PyTracks.
Everyone hearing me? Is it okay? Yeah? Yeah, all right. So now for the IT part, right? Okay, this is 1, this is 2, so I can open Kaja here. And then events. Presentation, okay. Control Shift, sure. This one is F5. Okay. All right. Thank you all very much for being here. I'm doing some. Okay. Go. Okay. All right. I'm Alex. Thank you very much. To start, could we talk a little bit about geophysics? Okay. It's this one. Let's discuss the fish-on-track method, which is a method to establish the age of a certain region of the Earth. Okay? All right. To use this method, researchers need certain materials, certain minerals from that region. You want to date the region, they need the minerals from that region, such as apatite or epidote. I have samples of them here, so could you please check them and show it to your friends, okay? All right, so the kind of round one is the apatite, and the ones that look like charcoal are epidotes, okay? Okay, so what does these minerals have in common? Okay, they have uranium as an impurity on it. So these, since this uranium is unstable, it decays by spontaneous fission. Right? So it liberates energy. So you have two fragments that displaces these atoms and then melts the structure of this mineral. When this happens, they cool really quickly. So you have a piece of a track that we call track, right? So you have this this mineral chemically etched, and then you can see these tracks under an optical microscope. Okay? So, okay. So this is one of the equations that we can use to determine the age of these minerals. So let's take a look of HOS and HOI there. Okay. The HOS and HOI represent two different densities of the minerals. HOS is related to the mineral we want to know the age, and HOI is relative to an external detector that we put there at some point on this to get the tracks that are being traced on a certain detector, right? Okay. So you have these two detectors. The mineral and the detector, and HOS is relative to the tracks in the mineral, and HOI to the detector. Perceive that these tracks are really different. You have, for instance, there tracks in apatite that you're seeing there. There you have tracks in muscovite. There's a mineral that's used as a detector, and that are tracks in DAP, which is another detector, which is a plastic one. Okay?
What is the scale?
I'm sorry?
The scale.
The scale. This is around micro. Yeah, you have micro there. So, okay. So to use this equation, we need to check these densities, okay? What's the issue in that? Okay, this is one of the images that we use to work. So if you'd like to know the age of that mineral, imagine yourself counting like hundreds of images like that, just for one region, okay? So you have, for instance, 100 of images, 50 from the mineral, and 50 for the irradiated detector. Okay? So you count them, and you count several of them, and you put them in that equation. And researchers do that by hand on the microscope. Right? So? Yeah. And okay. So you can perceive also like how this is difficult to count because you're on the microscope and you have like lots of time to count this. So it's like on this image, on the first image you have like 100 tracks, and on the third one, on the the 51, you don't have that efficiency anymore, you know, because you get tired. Okay. So, okay, that's where PyTracks enter. So we're using scikit image, NumPy, SciPy, Matplotlib, and several tools that we're developing to make software that automatize that process. Okay. We expect to have this alpha version until the end of October, right? So you can put more or less 2 months in there. Okay. Okay. So quickly, let's discuss what does PyTracks already do on this field. So what do we have implemented already? So, for example, these are the tracks in that I showed. Now we have this algorithm that counts these tracks manually, automatically. Sorry, and in that paper you can see a method that we developed using Watershed to separate these tracks, because this is the main problem on counting these tracks. They're not that good yet, but we're getting there. Okay. Okay, if you'd like to check the algorithm, the code, the images we used, everything is available there.
Since the other presentation took a bit, I think I lost the first 2 minutes. Those are tracks of what? Those are holes in the material? What is the black spots?
Okay, where is the mineral? Everyone? Okay. Yeah. Please, could you see any, just one for him?
Yeah, sure.
Okay.
So it's a picture.
Yeah.
The material, and that's the holes.
Yeah. But that's micro.
Okay.
So, all right, you have the mineral, you have the uranium decays, you have a track, and then you put that on the microscope, and you see this, right?
Okay, thank you.
All right.
Now it's clear.
Okay. So the first problem for us was to divide these tracks, to separate these tracks that are together. Okay. Again, if you'd like to see algorithm, code, images, are all available there. That's not possible. Okay. So now for tracks in apatite. Okay, in apatite, as you can see, they look more like cones, right? So for cones, you have this structure, and we developed another algorithm that finds the end, the begin and the end of the track. So based on that, we can also separate some of them. We're getting there again. Okay? So again, the images that we use in this study, in this algorithm, the images, the code, everything is available there. Okay? We also have several tools implemented, like 3D representations of these tracks. We also have curvatures, different kinds of curvatures that can help us in another problems that aren't this one, maybe dividing cells and something like that. Okay? All right. We also have several shape descriptors for binary regions, like Fere, Malinovska, Blairabilisa, and everyone is represented there in our algorithm. Malinowska, for instance, is very interesting to us because it returns a very high number when it has more than one track in the region. Okay? All right, so now what we'd like PyTracks to do. Okay, so if we have row S and row I, we would like PyTracks to return you the age. Okay, just thinking, returning you the age. Every aspect that you see there, almost everyone is a constant. So we have some, just a little bit of work for doing that. No, don't do that, please. Don't do that, please. And okay, so for that, we can, the problem is this is only one equation for the age. We have several of them. So we have to implement some functions on that, not just one age function. Okay? So we'd like to use the 3D information for measuring these tracks. And using the descriptors, we'd like to recognize these tracks using machine learning. We're working on that. We're working now on the age problem. We have some results, and I can show you them later if you want. Okay? So, okay, some of the references that I'd like to divide with you. The first one is the watershed transformation that we use for separating the round or almost round tracks. Okay. The second, Velasco, Otsu, and Yen. Oh, sorry. Velasco, Otsu, and Yen are binarizations that we use a lot, and Wagner and van der Haat can give you anything that you want to determine the age of a track using this method. Okay? Thank you very much.
Questions?
That's not possible, man. No, this clock is running. No, that's not possible.
Thank you very much.
I'm stealing your time, right? So.